Welcome back. So, in today's video lecture, from now onwards, we will look at the module number 4, that is liquid solid interfaces. Okay. So, we'll first start with the overview of the colloids. Okay. We have taken colloid as a best example of liquid solid interface. Okay. We'll first start with some understanding of colloids, and then we can as we move on, we will try to cover the other topics that are listed under the module number 4. Okay, so let's begin. Right. So why one has to study the colloidal particles is something we need to understand, right, in this slide. So, let us say whenever we deal with the liquid solid interface system, okay, often that we encounter is the colloidal system. For example, you may deal with dispersion, emulsion, and various formulations, let us say in pharmaceutical industries, cosmetic industries, paint industries. So, we often encounter various in various applications we deal with the colloidal systems, right? So one or other the ways we always deal with colloidal system. So uh, which is a good example of liquid solid interface. Okay, so we have taken this system as an example, so that by understanding the concept of stability of colloidal system, we can understand various fundamental forces that are required to understand, to keep them stable, right, to improve the stability of the colloidal system. So that is why we need to understand the different types of forces, like van der Waals forces of attraction, electrostatic repulsion, the DLVO force, steric repulsion, and all those aspects is very important when we talk about the stability of colloids. Okay, from now onwards, we are going to look at the types of forces. That is from the fundamental point of view. You will also understand in a general case how you can compute the interaction between the pairwise interaction between two macro objects, planar objects. Later, you can apply the same concepts for between the particle system, colloidal system. Okay, it can be spherical particle, it can be non-spherical particle, but you will be able to still apply those concepts later on. So we want to as we move on, we will also look at several topics, like the electrokinetic phenomena, right, that is also going to be covered in this module. Okay, that is also very good example. There also we will look at the colloidal system, charged colloidal system, which is a very good example for liquid solid interface system, right, and why how we measure zeta potential and all those aspects. Okay, so what is known as electrophoresis, those concepts we will be able to see in this module number 4. Okay, and so the question that we asked to us, why we should understand colloid, that is very much important because we have chosen as a liquid solid interface. So we have chosen colloid as a good example of liquid solid interface system. Okay, and it is also useful, it will also be helpful in a way that we will be able to connect very well with based on the our day to day examples, right, that we often encounter, right, various formulations that we know very well, right. Say for example, dispersion, emulsion, right, and in these cases you will be dealing with colloidal system, and this is very good example of liquid solid interface system. Okay, so to start with, we will understand what is the importance of colloids from the perspective of liquid solid interface. So let us understand there are various advantages when we want to understand the when you want to study the colloidal system under liquid solid interface. So the surface area is drastically varied when we deal with the colloidal system. Okay, um, and the electrostatic concepts can be readily applied. Say for example, if we deal with a charged colloidal particle, okay, there is something called electrical double layer concept at the interface that we are going to look at as we move on. And so the phenomena in at least in electrokinetic phenomena, we will see how the jitter potential, right, uh, which is basically due to the electrical double layer at the interface, right, and how it influences the particle-particle interactions and overall system stability. How by measuring jitter potential one can comment on the stability of the system. Okay, that is something we can understand from the electrostatic point of view. There is something called surface charge, surface energy and stability. So basically when you deal with the system like emulsion where you have dispersed phase, like let's say you are dealing with oil water system, oil in water emulsion. So oil will be dispersed phase and water will be a continuous phase, and what governs the stability of colloids. So that is something very important when we talk about surface energy and stability. And what is the role of electrostatic and steric forces, okay, at the liquid solid interface. uh, how you can actually prevent the aggregation, right, okay, how you can improve the stability of the dispersion. So those aspects we can one has to study from the perspective of liquid solid interface. And adsorption. So let's say if we study the if you understand the role of the colloidal particle, okay, on absorb on in absorbing molecules, ions or surfactants at their surface. Okay, so where it is important is in water purification. You can use this colloidal system. This based on this absorption phenomena, we can try to uh, eliminate pollutants by absorbing them onto the colloidal surface. So by looking them in details about the absorption of the pollutants onto the colloidal surface, we can exploit these colloidal particles, right. So we can explore various possibility of the colloidal particles and its application in water purification, and also in drug delivery systems, right. So in drug delivery, what is so important is the how you can actually carry these active ingredients. So if the particle has good affinity to the towards the active ingredients, can this be absorbed onto the colloidal surface? In such case, colloidal particle can be used as a carrier, right. So that is so we need to understand. So there are various advantages, right, when we understand, when we study the importance of colloids, right, from the perspective of liquid solid interface, right, in details. Okay, so let's understand the some of the basics of let me try to give you some overview of colloids and particles. Okay, so as you know, colloid is a substance dispersed in a medium, and usually in the size range between 1 nanometer to few microns. Okay, right. This is the typical definition for colloid, right. So I have listed several examples, for you to relate, quickly. Say for example, if we talk about system, liquid solid system, liquid gas system. So we are talking about liquid gas system, but although this model is all about liquid solid system, we will also understand colloidal particle from other perspective. For example, liquid gas system, we know some examples like fog, mist, aerosol. So these are examples of colloidal system where here liquid is dispersed in gas. Gas phase is going to be the continuous phase. In the case of smoke, okay, the dispersed phase will be, although I have given here a question mark, the dispersed phase here will be solid, right? And in the case of foam, the dispersed phase here will be gas, right? And in the case of liquid-liquid interface system, although we mentioned emulsion, here you also have, unlike the surfactant, if you use nanoparticle or particle system, such emulsion is called a Pickering emulsion. So, in such case you can still put this system under the liquid solid brackets, right, under the liquid solid interface systems. So, this one is a good example of colloidal solution, where you have a continuous phase which is a medium, and dispersed phase is a solid which is nothing but colloidal particle, right. So, a good example is the dispersion or colloidal solution. Okay. So, if you want to understand, the milk is a good example of an emulsion, right. Okay. Because it contains about 90 to 92% water, and you have about fat and fat globules and protein particles. So, here fat globules are dispersed in the continuous medium, that is water, and protein particles are used as a stabilizer to stabilize these fat globules, right. This is a good example of emulsion. That is why you can't see this, although there are immiscible mixture, because these fat globules are readily, finely dispersed in the continuous medium, that is water, using the stabilizer called protein particles, right. That is why this milk is called as an emulsion, right. It is a good example of an emulsion. We talk about ink. Okay, ink particle is colloidal system, because the pigment and or the dye that is dispersed in water is colloidal system. Okay, it shows a good. You can see that this pigment particle, if you shine a light, you can see these pigment particles are scattered everywhere. So it can display, Tyndall effect. So this uh, system, can respond to Tyndall effect. Okay, and it can scatter the lights, right. So that's why this glowing color comes because of the Tyndall effect, right. Right. So that already. Let's say we. So here I have illustrated three best examples for you, right, to understand various systems. Let's say we talk about suspension. Okay, liquid solid suspension, right. And here the solid here is the particle itself. The spherical object given here is the particle system itself, right. So, it is dispersed in the medium called water, right. This is a good example of dispersion, and it is a good example of liquid solid interface, okay, right. In the case of emulsion, we talk about Pickering emulsion. Let us say Pickering emulsion means when we use particle as a stabilizer instead of surfactant, such emulsion is called Pickering emulsion, right. So, in this case you see that the droplet, let us say if you talk about water in oil or oil in water emulsion, here oil, these droplets are oil droplets, okay, but stabilized by the particle system or stabilizers, right. So, this spherical object represents the droplet only, but around this droplet the particles are also confined to the the particles are acting as a stabilizer, and they stabilize these droplets, right. So, this spherical object as such is a droplet, okay, but the particles are part of this spherical objects, that is a droplet, right. The third one is the foam. Here it is good example of liquid gas system, okay. So, here the spherical object is nothing but a bubble, okay. It could be nano or micron sized bubble stabilized by the particle system. Here the spherical particle or particle is part of the bubble shown here, right? And the bubble is a dispersed phase, which is nothing but a gas phase dispersed in a medium called liquid. So, this is a good example of foam. I mean, foam is a good example of liquid gas system. Okay, right. So, where are these colloidal system? I mean, colloidal particles are applicable. I mean, the application. Where are these uh, particle system? I mean, where we can use these colloidal systems, right? That is the question that we are asking now. So, it can be you can see that there are various applications, as in emulsion in food, cosmetics, and pharmaceutical applications. Okay, and these are emulsion droplets, SEM images of emulsion droplets, right? And what is shown in the schematic is a foam. It's a good example of liquid gas system. Like we have seen in our module number 2, okay, when we dealt with the contact angle, surfactant and all, we described that the contact angle is just like HLB number that we define for surfactant. The contact angle is very important for the particle system, because that is what decide whether it will stabilize water in oil emulsion or oil in water emulsion. Okay, so theta or contact angle or theta is very important parameter, right, in this context. Okay, so you know what is emulsion, Pickering emulsion, foam, and this part of this equation, that is gives detachment energy equation. We have also discussed during module number, I think, 2, right? So, and this equation signifies that as a function of the size of the particle, if the size of the particle goes up, the Gibbs detachment energy also goes up, and it can also be controlled using the theta, that is contact angle of the particles, right? Okay, so just to give you another example, let's say silver nanoparticle of size less than 100 nanometer dispersed in paint is used as antimicrobial coating in hospital setting. This kind of coating is developed to uh, you know uh, to eliminate, or to to prevent the microbial and bacterial from the bacterial diseases, right? So, in hospital setting, this kind of special coatings, right, paints are applied on the wall, so that these paint can act as a antimicrobial coating, right? It can keep the surface away from the bacterial and uh, you know uh, other microorganisms, right? So, that is the one important. This is actually the latest latest development, right, that took place in paint industry, right? Yeah. So, what is colloidal stability is very important, that we are going to address now. So, in understanding the colloidal suspension, emulsion and all that, what we are trying to emphasize is that it is important for us to let's say prepare a stable system, whether it is an emulsion, whether it is a formulation, important formulation. Okay, whether you want to maintain a good shelf life of the product. So, in every aspects, what is very important to address is uh, what is the colloidal how you can maintain the stability of colloidal system or suspension or dispersion, right? So, that is the question. So what is causing them to attain that stability is the coagulation or dispersion. Okay, this is because of the aggregation tendency driven by the van der Waals force of attraction. So, whenever there is van der Waals force, take act, between particles take place, there will be they will tend to aggregate, right? So we want to avoid such aggregation. So by means of some uh, counteracting force, right? So one such force is the electrostatic repulsive force, right? That actually this electrostatic repulsive force will help uh, achieve the required stability, right? So it can overcome the aggregation, right, which is caused due to the van der Waals force of attraction. So when the electrical double layers of two particles overlap, we are going to look at different double layer model. There you will understand what is known as the electrical double layer overlap, okay, and the electrostatic force results. So it can be if it results in electrostatic repulsive force, it will prevent or it will overcome help us overcome the aggregation and all those aspects, right? So it serves to counteract the attraction due to van der Waals force, right? So this electrostatic force is very important to counteract the attraction due to van der Waals force. And mm, so this electrostatic force depends on the charges of the system, okay, and if you tune the charges of the system, you can tune the electrostatic repulsion, electrolyte of the medium, okay, and separation distance. These things we will see, these are the parameters that govern the electrostatic repulsion. On the other hand, you can also understand maintain stability by imparting the steric stability, right? So let's say if you have particle system and there is some polymer that can absorb on the particle surface, okay, and by adding the polymer into the colloidal suspension, we can actually improve the repulsion, the stability of the system, because this polymer absorbs on the particle surface, and what will happen is they will this polymer layer mask the attraction, okay, and provide a repulsive force due to steric effect, because when polymer layer is formed around the surface, let's say if you have particle surface here and you have the polymer brushes, okay, when you grab these polymer brushes on the surface of the particles, so basically what happens is that when two particles come very close to each other, and there will be overlap, right? The polymer molecules will overlap, and there will be a steric hindrance that will not allow the particle to come very close or penetrate uh, further. So this will act as a repulsion, right? It will provide repulsive force, right? So due to this steric effect, so because this repulsive force is generated due to the steric effect, we call such force as steric repulsive force, right? A repulsive force due to steric action, right? Right, or steric hindrance, right? Here the role of polymers in a dispersion is more complex. Uh, Although it is one can improve the stability, but it is very important to understand the interaction between particle and polymer, and sometimes it becomes very complex system, okay, right? So here if you can look at the stability of colloidal system based on the electrostatic force, right? Let's say if there are when two charged particle come closer, right, as they approach each other very closely, they will experience, right, they will experience different forces at different surface to surface separation distance between the particles, right? So so the best example of kinetically stable system will be when they go through this profile, right, compared to this one. If you look at here, the secondary minima and primary minima, whenever particle reaches this distance of separation, okay, there will be a primary minima, and when it goes through this primary minima, there will be irreversible attraction. Due to irreversible attraction, there will be aggregation. Okay, once the aggregates are formed, it is very difficult to separate them, right? So what is important to not driving them up to this point is to increase this barrier. This is primary maxima. Okay, if the barrier here is increased several fold higher, then what will happen is this particle will not reach the this primary minima at all, right? So there will be no question of aggregation or coagulation at all. So for that, so the electrostatic repulsive force between the particles, if it is very much pronounced, right, then one can avoid the or prevent the aggregation or agglomeration, right? So such system is called kinetically stable system. Okay. So here it is given this primary maxima, this barrier, is in terms of kBt is given. So if the barrier, the energy barrier is several times greater than the kBt, which is the thermal energy, then the particle will not be driven up to this point, that is the primary minima, right? So such system is called kinetically stable system. So a good example of aggregates of gold nanoparticles given here. This is TEM images, right, of gold nanoparticles. You can see that different aggregations of gold nanoparticles, right, different sizes. Okay, so because of the huge surface energy, these nanoparticles develop a tendency to aggregate each other. When they aggregate, they form a fractal like structures, right? Fractals or aggregate structures. The disadvantage of these aggregates is that the aggregation diminishes the optical properties of gold nanoparticles, right? Or its catalytic properties are reduced by the aggregation of these gold nanoparticles, right? Yeah. So this is the TEM images of gold nanoparticles. That is what shown here. So let's ask a question: why colloidal stability is important? Okay. Uh, it is essential to ensure that the dispersed particles remain uniformly distributed within the continuous phase, right? And without aggregation, sedimentation or phase separation. So we want to avoid aggregation, sedimentation, sometime creaming or phase separation, right? So for that we need to improve the stability of a colloidal system. So it is also important for various other practical applications. There are 3 points I have listed. One of them is to maintain functional properties, right? If you want to maintain the functional properties, we need to avoid this aggregation and sedimentation. Okay. So why we need to maintain functional property? Because if you want to extract the actual function from the various products like paints and cosmetics and pharmaceuticals, we need to retain this functional property so that you get a desired performance output. Okay, the loss of stability, so that is important. Shelf life, so if you want to improve the shelf life of the product, one has to uh, avoid this aggregation and all those things, right? And prevention of phase separation, this is also very important from the perspective of the finished product, right?